Hello, hello. Yeah, still next Friday. Okay, so let's start. Do you have any questions before we start? All right, so yep, so second midterm is next Friday. Same format as last time. Same format, meaning, there will be two instances of the exam, one for the lockdown browser and one for the submission. And you will take the exam on the lockdown browser and then you will submit on the submission instance. You are allowed to bring one page of note, one-sided as last time. Okay, so the materials will be from wherever we stopped since midterm 1 to midterm 2. So that will include Khmer Railbound, will include the whole chapter on confidence intervals, and then a little some part of the hypothesis testing. So specifically, that would include things like, type 1, type 2 error, right? No alternative, rejection region type of thing. So if you want to, right? So basically that's, I think, chapter 11. If you want to know what is not included in hypothesis testing, the two topics not including would be Neyman-Pearson lemma, which we may mention today, but because I think that will be, a little bit more complex for you to digest, so I won't put that on the second midterm, and the likelihood ratio test. So in chapter 11, these two topics, which are two sections, I think, won't be covered. The rest will be, so it's chapter 12, right? The rest on hypothesis tests will be there. And there are just, basic questions on certain types of rejection regions, type 1, type 2 errors, that kind of thing, and, testing your understanding of these concepts. Any questions on these topics? All right. So similar to last time, the quiz of this week will be taken, right, from the materials of the previous midterms. So again, you can submit it this Tuesday, and I'll post the solution, to the whole midterm on Tuesday by the end of the day. Or, I mean, I'll post on Wednesday, I guess. Or you can submit on Friday, and I'll, just post the parts that are not included in the quiz. Last time we went with the option of submitting on Tuesday. Anyone wants to change their mind on that? Okay. So still Tuesday then. Any objection? For this week, right? I mean, yeah, well, next week's quiz, whatever you want. I mean, yeah. So not the one due today, right? The one coming up. Yeah, quiz 9. Okay. All right, so no questions on these. All right, very good. So let's continue with where we left off last time. So last time we were, yeah, I can make it on Monday if you want. Is that what you prefer? But that said, right, the homework of this week, right, on hypothesis testing, whatever, may still kind of be relevant for the exam. So you don't want to wait until after the exam to try the homework. Okay. So let's continue. So last time we were discussing, right, the idea of hypothesis testing, where the basic setup, right, is we have, some kind of IID sample with some unknown, let me just say, right, distribution for now. The degree of, being unknown for most of the time for us will depend only on an unknown parameter theta. But a lot of times, I mean, not a lot of times, but it can be extended to the distribution itself being unknown, and that can still fall under the context of hypothesis testing. Like you would test whether the distribution is a normal distribution, or I don't know, like a t distribution, for example. That can be, also under hypothesis test. For us, right, the unknown degree will most likely be limited to the unknown some unknown parameter theta. So we have the null and we have the alternative. For example, let's say theta equals to theta 0. This is theta equal to theta 1 would be one possibility. Theta not equal to theta 1, etc. Okay. Our goal is to come up with a critical region C, so that, right, I mean, actually that's it really, right? Width size alpha and minimum beta, okay? So to remind ourselves, right, alpha is the type 1 error. which is a probability, right? So C, the critical region or the rejection region, means that if C happens, if we are in C, then we will reject the null hypothesis. Okay. If we are in C, then we reject the null. So alpha, right, is when the null is true, but we are in C, so we reject the null. And which is also the definition of the size of the test, or the size of critical region, just the type 1 error. Type 2 error is beta, which is the opposite. So the alternative is true, but we do not reject, right? We are not in C, so we do not reject the null. So we are not in, our decision is not to reject the null, so we make an error. So we saw that, right? We observed that alpha beta cannot be minimized at the same time. And actually, you know, when you look at this, it's kind of easy, because C and C complement are just opposite, you know, directions. If you want to make alpha small, that means you want to make C small, but then C complement will be big, and so beta will be big. Okay. So the philosophy, right, is to fix alpha, fix tolerance alpha, like 0.05, 0.01, and then among those, right, tolerance, then we will try to pick the C that would have minimum beta. So maybe, right, let's look at an example to bring all this, make all this more specific. Let's say that you have x1 up to xn IID, normal with mean mu and variance sigma square. For simplicity, let us assume that sigma square is known. Just to make things simple at this moment, we just want to kind of play around with the concept of type 1, type 2 error. Let's say that our null is mu is equal to 0. And let's say our alternative, okay, is mu not equal to 0. Let's just do that for now. All right. So the context, right, is that you have access to this IID sample, and you want to, based on a sample, right? I mean, you want to come up with a critical region that is based on a sample, so that, you know, you can accept and reject if, you know, if we are in a critical region or not. So what type, right, of critical region can we do? Well, actually, you know what? Let me do this just to make it easier and also highlight some things. Let's say that h1 mu equals to 1. So we could have, and by the way, right, from the last discussion, I hope you see that on its own, there's no restriction on critical region. Just the same way as like on its own, there's no restriction on estimators. The definition, the concept. So when we say something is an estimator, we can pick any you know, arbitrary thing that we want. At the end of the day, right, comparing different estimators and then see how they perform against each other in terms of biasness and efficiency, right, is what counts. So same thing here. Right off the bat, in terms of concepts, there's no restriction on what kind of critical region you can come up with. Right. The bottom line is, how do we compare different critical regions? So for example, let's say C1 is x bar bigger than 2. C2 is X bar less than -1. I'm not sure if anyone will even like to do something like this, but let's just throw it in, right? Who knows? People may even come up with that. And let's do C4, which is, let's say, S squared bigger than 5. Okay. So these are all critical regions. These are all possible critical regions, right? So the problem, right, is this. I mean, it depends on what problem it is. But if we stopped here, this is what is given. These are given. Okay, you're given the sample, you're given the supposed distribution, you're given, right, the hypothesis. Your task is to come up with some critical region. So you could think of this as, 4 different statisticians proposing 4 different critical regions, or one statistician, right, thinking of different critical regions they can try, right? So again, this illustrates the point that there is no restriction on what critical region you can use to begin with. Any of these conceptually can be critical region. Meaning what? Meaning that, right, statistician number 2 say that as long as the sample average is less than -1, I will reject the null and I will accept the alternative. Statistician number 4, yeah, says that if the sample variance is as long as it's bigger than 5, I will reject the null and accept the alternative. Now, of course, right, intuitively, you found that this and this sound a little bit off. But that's the whole point of discussion, right? Why is it off? Can you say, right? Can you give a criterion that compares these 4 critical regions? Okay. Because, I mean, the point is here, right? The goal is to come up with a critical region. So philosophically, your only restriction is to make sure that the size of critical region is alpha. All right, so maybe let's do that first. What are the type 1 errors for these regions? How would you do that? What's the type 1 errors of C1? If you have to calculate type 1 errors, what is it? Let me make it even more easier, all right? Let's just do this. Let's just make it 1, so everything is clear. Sigma squared equals to 1. What's type 1 errors for C1? Well, again, what's type 1 error? Type 1 error is probability that you are in C1 under a norm, which is X bar bigger than 2, mu equal to 0. Yeah, something like that, Alice. Yeah, I think so. But yeah, I mean, you don't have to even go there, right? No, not really. Actually, I think you forgot to discount for the sample size, because actually, right, what is X bar? X bar is normal 0 with variance, right? Sigma square over n, because it's 1 right here, is 1 over n, bigger than 2. Where, right, we have incorporated mu equal to 0 into the calculation, okay? Which is probability that standard normal is bigger than, I guess, 2 square root of n, right? And that, I think, is what we call z whatever, right? Are we okay here? how do I get to normal? Yeah, because I assume, right, this is, again, this is given. This is my sample. My sample is IID normal mean mu variance 1. So what is X bar? What distribution does X bar have? X bar is normal with mean mu and variance 1 over n, right? And under the null hypothesis that mu go to 0, then you got 0, 1 over n. Is that okay? Any question on this? What about type 1 error for the other guys? How about alpha 2? Alpha 2 then is right, which is oh, it does, right, Madhav? It does. Right here. No, it's fine. It's hard to keep track of everything here, but yeah, that's the whole point. If, right, I don't use that, then in general, right, this is this and this unknown, right? The true distribution X bar is unknown, but under the null hypothesis, then it's going to be normal 0, 1 over n. Is that okay? So, right, that would be standard normal less than what minus square root of n, right? Which is, I think, what we call z 1 minus, hold on, what do we want called? 1 minus, right? Probability of this less than that. Oh, you know what? What am I saying, right? This is not z alpha over 2. What am I saying? Whatever that is, z alpha. Sorry, I mixed up the notation of the score and the thing. This is it, right? This is it. I don't know. We just look at whatever that is. Sorry, that's it, right? There's no further notation on that. Sorry, right? It's just this and this. Okay. Because z refers to the percentile. This is not percentile. This is not percentage. This is it. We stop there. Sorry. So for example, right, I hope it's clear which one is bigger, alpha 1 or alpha 2. Which one is bigger, alpha 1 or alpha 2? Alpha 2, correct, right? So in this test, for example, I mean, if you just purely look at, and by the way, right, what am I doing? I'm looking at type 1, type 2 error. And when I said, right, how do we compare these these critical regions, right? Obviously, type 1, type 2 errors are what we used to calculate, to compare, right, confidence intervals, okay? Sorry, critical regions. So alpha 2, right, clearly is larger. So if you just go off on alpha alone, and because you restrict, right, you say alpha must be of certain thing, certain size, right? Which size alpha? Then maybe, right, that you won't choose this, right? You won't go with this critical region. So that's fine. Let's leave it, and we'll go back to that. What about alpha 3? right? Is alpha 3 promising? Sorry, is C3 promising? Right? You test mu equals to 0, mu equals to 1, right? So you will reject the null if the sample mean is equal to 1. What's alpha 3? It's not a trick question, really. Maybe a trick question, but it's not a big trick at all. What's alpha 3? Yep. Right, because it's a continuous random variable. There's no way it's going to take on value 1. I mean, there's zero chance it'll take on value 1. But okay, so isn't that wonderful? Right? C3 then is the smallest alpha possible. Then should we just even stop here and say, yeah, let's just go with C3? So right, in designing this test, right, we will use this critical region. C3 is the best. Agree? Yeah, we will. We will. But so, I mean, I don't know, whatever this is, it cannot get to alpha equal to 0, right? So should C3 be the best? Well, okay, I mean, so let's look alpha 4. Alpha 4 is, yeah, exactly, right? Actually, what's beta here? What's beta 3? Yeah, exactly. Why? So, by the way, right, let me ask a general question. Yeah, so let me ask you a general question. In general, alpha plus beta is equal to 1. Is that right? Type 1, type 2 error add together must be 1. Is that right? The answer is no. All right. So, I mean, what you said here is still correct, Alice, but I'm not sure complement is exactly it. The reason, all right, and I'm not sure because this can easily slip into your mind, and you might think that alpha plus beta equals to 1. Is not true because even though C and C complement, of course, are complements, these are calculated under different hypotheses. Okay, so if somehow this is the quantity, then yes, this plus this is equal to 1. But these are calculated under, okay, different hypotheses. So no. So like I said, right, usually alpha is 0.05, beta is around 0.40. They don't add up to 1. Also, if they add up to 1, then, right, this goal right here is pointless because the moment you know alpha, you will know beta. There's no chance for you to minimize beta. Okay, so alpha plus beta is not 1. They are not complement. C and C bar are complement by notation, but alpha and beta are not probability of complementary events because they're under different hypotheses. Is that okay? That said, right, beta 3 here is still 1. Why? Because beta 3 is probability of C complement, right? C3 complement, which is what? X bar bigger, not equal to 1, condition of mu equals to 1. But given a random variable, continuous random variable, What's the probability that it does not take on value 1? One, right? So this is because of the weird way, all right, that C3 is constructed. Of course, I mean, this is asking in general, right? There are some peculiar case where they add up to 1, but, all right. So C3, for that reason, right, is a really bad choice, okay? I mean, it's not good by any chance, but you know why then C3 is bad, because its beta is 1. You always make type 2 error, right? You always make type 2 error, meaning if the alternative hypothesis is true, you will never reject it. You will never reject the norm. So you will never go to, if the whole alternative hypothesis is true, like somehow if mu equals to 1 here, you will never recognize that with this rejection region. That's bad, right? So again, right, this is exactly where you need to understand the whole philosophy of hypothesis testing, that we cannot avoid alpha and beta, meaning we cannot minimize them at the same time. On the other hand, going with the extreme, meaning 1 is 0, 1 is 1, is also terribly bad, right? I mean, I guess that's everyone would agree with that. The middle ground, where alpha is small and beta is reasonable, is the best that we can aim at, right? Meaning, I mean, again, go back to the court example. Suppose that, right? I mean, this is equivalent to saying, right, that a jury would always say that everyone is innocent, right? Everyone is innocent. That means, right, every guilty person will go free. Is that good? I mean, your pick, right? I don't think that's very good. Is that okay? All right, so any question on this? So alpha 4, yeah, alpha 4 is what, right? Alpha 4 is probability that S squared is bigger than 5. What is alpha 5 here then? Well, what is the distribution of S squared? We got n minus 1 S squared, right, over sigma square, but sigma square is 1 here, right? So just do 1 here, just to show it, bigger than 5 times n minus 1. And so what is this? This is probability of a chi-square with n minus 1 degrees of freedom. It's bigger than that. Okay, whatever that is. Any question? Good question, Alice. I don't understand the last part. What do you mean by probability of correct rejections? What is that in terms of our, you know, C and H node, that kind of thing? I mean, I like the fact that you try to play around with these concepts. I just don't think there's a hope to relate alpha and beta in general. Because again, right, what you're proposing is probability of C under the norm plus probability of C complement under the alternative plus something else. And so you would like to compensate for that something else, right, to make it 1. It's great. You should play around with this kind of thing. But, you know, from a, you know, a little bit more calm, right, looking at things, you know, because these guys can be anything, right? I mean, it just depends on how the test is set up. So I don't see how abstractly these guys can be related to begin with. So I'm not sure you can do that. I mean, pure guess, pure gut feeling. Because again, right, it's really whatever this is here would have to somehow play around with the interaction between H0 and H1. it's unclear to me what needs to be filled in there. Is that okay? Yeah, I like what you're thinking, and definitely, it's great thinking. I just don't think it will be fruitful. And also, right? I mean, meaning wise, and exactly this is this, right? Statistics, by the way, right? I guess a lot of you guys are already feeling, tired of statistics now, but it's hard exactly because conceptually, you got to separate things out. You got to know when to use what. So in my opinion, right, alpha and beta, the reason why I ask this is they are completely different. They are basically probability under two different worlds, right? Two different scenarios. I mean, we said that H0 and H1 don't have to be complementary. But on the other hand, H0 and H1 should not have anything in common, right? I mean, if they have anything in common, that's weird. But they're not complementary in the sense that, universal wise. But for that reason, because they don't have anything in common, right? Alpha is what happens in the H0 world. Beta is what happens in the alternative world. Conceptually, flavor-wise, I don't see, a point to relate them. There is a relation, right? Their relation is exactly via the critical region, size-wise. But like connecting them beyond that, I don't know, right? I'm not discouraging that. I just don't see a meaningful approach there yet. Okay. Cool. Any other question? All right, so that's alpha 4, right? That's alpha 4. So let's see this, right? Let's say this, right? So, and by the way, right, these are just 4 things I can come up on top of my head. Someone else can come up with, a 5th or 6th one, right? So, but just let's focus on these 4 for now. All right, that's exactly the question. Yeah, what happens to that? You tell me, Jeton. Exactly, that's a great question. I'm going to ask that next. What happens to it? So to answer that question, right, again, this is why chapter 8 is so important. The distribution, right, the sampling distribution always comes back to haunt you, right? What is the sampling distribution of this? What's the sampling distribution of n minus 1, s squared over sigma squared? Well, let me answer a question for you, right? It's chi-squared n minus 1. But the crucial question in this context, though, is not that. Is does this answer depend on the true mu? Exactly. So what happens to the mu here? It just got dropped. Right? But the fact that it got dropped means what? So the fact that it got dropped, right, explain, I guess, maybe the peculiarity of C4, maybe. So how would you view C4 here, right? Suppose that someone, I don't know, who is quite creative in stat, right, say, I want to use C4. How would you tell that person your opinion on C4 versus C1 and C2 and etc.? I guess, right, everyone's gut feeling is C4 is no good. But why is C4 no good? Exactly. Or, I mean, is it clear that C4 is no good, or am I just kind of misreading you guys here? I mean, if you don't see why C4 is no good, also you ask, right? I assume intuitively everyone sees the C4 is no good, but exactly why is C4 no good? Exactly. It's no good because it's independent of hypothesis. right? I mean, in that sense, it's also independent of mu1, h1. So actually, C4 is kind of like what I said last time, where in a jury duty question, right? Someone says that a person is guilty if they wear a dark suit. I mean, sure, you can go with that critical region, but that's irrelevant to the question at hand, right? Which is this. Okay. But that actually is the next layer. But if you really want to push it, why is it no good? Because why is independent of the hypothesis no good? Why is the fact that it's independent of mu no good? Why? I mean, someone can still press that, right? Okay, so it's independent of mu, so what? Why is it no good? So always remember our goal, right? Our goal is to, quote unquote, even though this is unachievable, but still, roughly speaking, is something along this line, right? Minimize alpha beta, or if you want to be more precise, keep alpha small and minimize beta. Okay. Can we do that with C4? Or let me ask you this, right? What is the relationship between alpha 4 and beta 4? Yeah, you mean they add up to 1, correct? Right. So this is exactly one case, right? Together with the third case where they add up to 1. But why is this true here? It's exactly true here because it's independent of the hypothesis. So whatever I said about, right, depending on the hypothesis doesn't apply. So that's why they really add up to 1. But is the fact that they add up to 1 good or bad, right? I mean, somehow if you really want to be comfortable with your own knowledge, you feel like, wow, this is cool, right? But actually in our goal, is it good or bad? Is bad, right? Because that means the moment you set alpha, your beta is fixed. You cannot fix alpha and minimize beta. So in other words, right, if you, with the type of C4 region, right, you can fudge this around, right? You can fudge this number 5 to get it to like, to get alpha 4 to be 0.05, right? You can get alpha 4 to be 0.05, for example, when you choose this to be, some, right, reasonable number. But the moment alpha 4 equals to 0.05, what is beta 4? 0.95. And that's why C4 is no good. Is that okay? Any question? All right. So let's not say mu, right? Mu is this particular question, but your hypothesis can be anything, right? Your hypothesis can be about sigma square, can be about all the stuff. So the right statement is when the critical region is independent of the hypothesis, then alpha beta add up to be 1. But I mean, I hope that seems obvious, right? Because what you're saying is this: probability of C given H0 plus probability of C complement given H1. But if they're independent of the hypothesis, then that's exactly why it's 1. But right, the right statement is independent of hypothesis. I mean, it just so happens that I just pick an example on mu to help you guys play along with the concept. Mu is not, something particular here. Is that okay? Yeah. Any question? Yeah, actually, if the hypothesis is about sigma square, for example, I mean, I guess 0 here doesn't make sense, but 2 or whatever. then which one is problematic? Which ones are problematic? I mean, these guys, right? But I mean, again, right? I hope that in some way my discussion here is kind of a truism, because when the hypothesis about mu, right, sigma s squared has no role because s squared is the estimator on sigma squared. But again, right, statistics or math in general is in some way a translation of what we feel intuitively into something precise. That's all there is. So what we feel, right, is this one's no good. But precisely why it's no good is because the alpha and beta, right, are fixed in a certain relation that is undesirable for our goal. So again, right, you know, all in all, right, we value statistics, we value math because it can allow us to make statements precisely, not just intuitively. But so, you know, but on the other hand, right, I hope you don't feel like what I'm discussing here is something, you know, earth-shattering or anything like that, right? No one would do that to begin with. But you kind of want to clarify for yourself why that's true to begin with. Okay, question? All right, so then, right, I mean, I guess these guys are out easily. Then that leaves us with these two. And right, because of my choice, you observe that, we write down here somewhere, that alpha 2 is bigger, right? Alpha 2 is bigger than alpha 1. So that seems to easily, right, make the C1 the winner. But let's make things not as easy, right? Let's do C5 to be x bar less than -2. All right. Then I hope it's clear that alpha 1 is equal to alpha 5. Right? So what's the point? Which one is good here? Or both of them are fine? Which one is better, C1 or C5? Which one is better? I mean, just intuition here, right? There's no trick really. Look at the context. What's the what are we testing? What's the alternative? So, right, I mean, again, I guess symbols, you have to read the symbols, but also don't get trapped in the symbols. Take a step back and see what the context is. You're testing the true population mean is 0 and true population mean is 1. The first proposal say that you reject, right, or you accept the true population mean is 1 when the sample mean is bigger than 2. The second proposal say that you accept, or right, the true population mean is 1 if the sample mean is less than -2. Which one sounds reasonable to you? Which one sounds strange? Again, keep in mind that X bar is supposed to give you information about mu, right? X bar is mu hat. I mean, that's still true. So which one is better and which one is strange? C1 should be better, right? Because mu is bigger than 1. Sorry, mu is equal to 1. So the direction is right in this direction, that X bar bigger than 2 is the right direction. Is that okay? So you would expect a C1 to be better, or at least C5, actually nonsense. If you see a negative sample mean and you go with mu1, then Yeah, I said a lot of things. I don't know what I said. Basically, all I'm saying is, right, look at the direction of the hypothesis. Mu is equal to 1, right? Meaning it points the true population mean to the positive direction. I mean, that's that. So if you say that if the sample mean is negative, then I will go with the population mean being positive. That's super weird, right? So in other words, and here, right, C1 says if the sample mean is positive, I go with this. So C1 should be expected to be better than C4, C5. If C5 is better than C1, I think the world is in, some kind of weird dilemma. Okay. So that's just arguing out by intuition. How would you make that precise? Because alpha 1 is equal to alpha 5, right? How would you make this precise? How would you convince everyone that C1 is better than C4, C5? Exactly. Yeah, that's it. Right? You would definitely expect beta 1 to be, in fact, much less than beta 5, much less, right? I mean, if beta 1 is bigger than beta 5, again, we're in trouble. All right. So let's do that, right? What is beta 1? So again, remember, right? C1 is X bar bigger than 2. C5 is X bar less than minus 2. What's beta 1? Right here. This is alpha 1, right? This is alpha 2, right? And you see, I mean, the reason is this is because this is 1. So if I make this into 2, this is a 2, and by the symmetry of the Z distribution. What's beta 1? Well, it's going to be the probability of X bar less than 2, right? C complement given mu equals to 1, given H1, which is the probability of, right, normal with mean 1, variance 1 over n is less than 2, right? Which is probability of subtract 1, right? And then multiply with square root of n. So standard normal is less than subtract 1 and multiply with that, so less than square root of n. Is that okay? On the other hand, what's beta 2? Beta 2 is probability of X bar bigger than minus 2, right? Given mu equals to 1. Which is probability of normal 1 over n. Oh yeah, thanks, beta 5. Is bigger than 2, bigger than minus 2. Subtract 1, right, and multiply with that is probability of Z bigger than minus 3 root n. All right, so what's the comparison between these two guys? Which one is bigger? Is it clear that beta 1 is less than beta 5? All right, cool, right? So again, now I guess, right, from your question, I guess that maybe it's still unclear to you yet. Maybe you're just not used to this, that C1 is definitely better than C5. And by the way, right, the reason is, I would like to say, and trust me on this, is quite simple, because mu equals to 1, you definitely do not want to go with this. So a lot of these examples I give, right, so it's several points. First, I just want to demonstrate what critical regions are. They're just rules you come up with to reject, okay, or accept. Second, right, there's no restriction on what they should be, but based on our criterion, right, we should be able to compare them. And the ones that come out the best should be the one that's most favorable. Sorry, makes most sense. Okay, I don't know. It feels to me like if you tell me that any of these guys win over C1, I would feel super strange. Now, obviously, suppose between C6 like this, x bar bigger than 3, and C1, x bar bigger than 2, which one is better? Then, you know, that's unclear, right? You see that C6 and C1 don't have a direct comparison. How does the alpha compare between alpha 1 and alpha 6? So just remember, alpha is a probability of the C, right? Probability of the critical region. Which one is bigger, C1 or C6? Which one is bigger? Yeah. So how do they compare? How does alpha 1, alpha 6 compare? Alpha 1 will be bigger than alpha 6, right? Yeah. But then how about beta 1 and beta 6? So which region is smaller in terms of complement? Or I guess now you know, right? Beta 1 would be less than beta 6. So that's why there's no direct comparison between them, right? So exactly, right, at the end of the day, the issue is to decide which level you prefer. And that's exactly, it has to do with the tolerance, the size, right? You would pick the tolerance so that it will hit exactly the level you want. But so, you know, the story of this is a story of the types of critical region you can come up with, meaning the structure, right? So what I'm saying is, like, again, this is a very simple problem. So the structure should be clear, something like this, all right? If you come up with any other structure, it would be inferior. But among the types with the same structure, then you don't know, because it's just, you know, the matter of fudging the alpha around. Then you want to pick the right level to do rejection. Is that okay? That's a message. Any question? Okay, so let's do example 12.2 from the book. And from this, you probably will see everything is clear. This example will be very easy, but I think it's nice, so you understand what's going on. So the book, right, just doesn't write like this, but let's say x1 up to xn is IID, normal with mean mu, and variance 1, okay? And they say the null is mu equal to mu 0, the alternative is mu equals to mu1. And they say that mu1 is bigger than mu0. Okay, that's what the book says. They say find k so that x bar bigger than k has size. So this is the critical region, right? C equal alpha equal to 0.05 for, that's it actually, with size n, that's it. Okay, so that's 12.2 example. Now you see, right, that, okay, it's a decent problem in itself, but you see behind the scene, right, I hope this discussion that I just did shows you that why, right? The book immediately noticed, right, this is not innocent. This exactly is constructed based on what? Based on the relation that mu1 is bigger than mu0. Is that okay? So this relation exactly is because of that. Now, right, I mean, admittedly, the question just asks you to find k. But, right, if you just approach this topic, you would like to ask why no other shape or structure is possible. And the reason is exactly on this discussion over here. And the question of looking for k is exactly the question of deciding between 2 or 3 right here. Is that okay? So let's do that, right? But I think this is fine. So what do? You say probability, right? Alpha is probability x bar bigger than k, conditional no. Which means probability x bar bigger than k, conditional mu equal to mu0, which is probability of a normal would mean mu0 and variance 1 over n. Because of this, is bigger than k, which is probability of a standard normal, right, is bigger than k minus mu0 times square root of n. And now, so I can rectify my mistake before. What this means, right, because this probability is alpha, this value right here about our notation would be z alpha. So our value of k is mu0 plus z alpha over root n. Is that okay? Any question? Then example 12.3, right, would go further and says, with reference to, yeah, thank you, Christine. That means you just plug in 0.05 here, right? I guess I didn't even pay attention to that. And that's why the book will give you 1.645 as your final answer. But really, right, I mean, actually, my answer here, any alpha would work. I mean, as long as you understand what the alpha is. Is that okay? Okay. So they say with reference to the above, right? Whoops. In 12.2, decide the min sample size, the minimum sample size. to test so that beta is less than or equal to 0.06 with mu0 equals to 10, mu1 equals to 11. Yeah, okay. You know, Madaf, I don't think testing your skill on reading a table is on my list of agenda. So in other words, this is the final answer I expect. Because, right, everyone knows what the alpha is, I hope. And, you know, nowadays we can just plug in Python, wherever. Yeah, no, it's fine. But, right, please, I'm not sure this sounds a little bit, you know, whatever. But reading tables, right, is definitely not math. I mean, it's a technical part where you need to translate something into a number. Definitely, you should be aware of, if I want to translate these to numbers, I can do so and so, meaning I can go on Python, I can, you know, do R, but your time, right, is better spent understanding the concepts and deriving the concepts and, you know, writing down relations. Okay, it sounds abstract, but it's not abstract nonsense. It's abstract sense, right? And again, right, if someone pressed you to say, okay, give me concrete numbers, and then you're like, okay, give me alpha, give me mu naught, I'll tell you. That's it. All right. Okay, so what is it? So how do we do this one, right? So this one is concerned with beta. So again, I guess this is immaterial too, really, right? It's just basically given a level of beta. So let's see, what do we do, right? What is beta in this case? So beta, right, is probability that X bar is less than K, given H1, right? Right here. Because this is C. So let me do in the abstract, all right? So this is just probability of, right, X bar less than K given mu equals to mu1, which is probability of normal mean mu1, right, variance 1 over n less than K, which is probability of standard normal is less than K minus mu1 times square root n. And then, right, I mean, understandingly, that you would plug in 0.06 here. I'll just solve it with beta. Is that okay? What this means, right, is that K minus mu1 times square root of n would be Z1 minus beta. Do you agree? Because it's less than. If you turn to bigger, then it will be 1 minus beta. Right? Now, what are we solving for? We're solving for n, right? Sample size. So n is Z1 minus beta divided by K minus mu1. What's K? K is from your previous problem, which is Z1 minus beta divided by mu naught plus C alpha over root n minus mu1. Is that okay? Absolutely. But so let me do this, right? For now, square root n. All right, because I have a question to ask. I have a question to ask. Yeah, Jeton, you're right. Okay. Any question here so far? Now, like I said, right? I mean, this is really hard for you to do. I understand this, but always be mindful of the context of the problem. It is exactly what will help you to distinguish a right answer from a wrong answer. Because if somehow your answer doesn't make sense, then however good you trust your math, right, you must go back and see, right, what's wrong, or maybe you just missed something. Because here, right, the reason why I don't go with what Jatin was telling me, which is right, is because right here, this is square root, right? This relation is correct. What that means is this number should be what? Negative or positive? This number better be positive, right? Otherwise, my answer is nonsensical. But what is the relation between mu0 and mu1? What is the relation between mu0 and mu1? Correct. So what sign do you expect this to have? This should be negative, right? Well, in case you say, well, the Z alpha will save you. Well, guess what? The square of n, the moment it gets big, right? Because I mean, there's nothing to prevent you from pushing the sample size to be large, right? So here, this is negative. Let's say, am I in trouble? Right? Because this is supposed to be a positive number, but here I'm having a negative number right here. I make a mistake somewhere. Well, what sign does this have? Hopefully negative, right? I like that spirit. Is it negative though? Yeah, I like both, right? You're right. Exactly. This is a good way of thinking, right? If we are correct, then this better be negative. Is it negative? How do we know? What is this? This is the quantile, right? Which is the one where the right area is 1 minus beta. Now, how big is 1 minus beta? .94, right? 0.94, right? Because I mean, here, like, I mean, beta is supposed to be small, whatever. So that means Z1, that would lend Z1 minus beta over here. Right? And so we're good, because this will be a negative number. So as long as 1 minus beta, right, is bigger than 0.545. And again, right, I mean, I guess so the problem is you want to push for beta small 0.5. So this answer makes sense. Any question? Are we okay? All right, so I guess this should cap the exam materials, right? So you'll be asked something like this, some topics on the exam. Maybe let me tell you one more thing, and then we're going to look at some code very quickly. So go back to this example, all right? Now suppose that instead of mu equals to 1, let me change it to mu positive, which I guess, right, is what you see more often. How would that change the discussion of what I do down here? If instead of writing mu equals to 1, I just change it to mu positive, so I'm still keeping right the side of the discussion. How would that change whatever right I was discussing with you so far? So the answer is this, all right? It doesn't change. What do you mean, Madhav? Parameter is never 0, right? I don't understand what you mean. Parameter is always mu. Under the norm, mu is equal to 0. I mean, parameter is never 0. 0 is not a parameter. I mean, mu takes on value 0 under the norm. Yeah. So, all right, the answer is this, that it doesn't change much. I mean, it would change something, but by the way, right? So what I'm saying is this. H1 mu equals to 1 versus, right, H1 mu positive. The difference is this. Then this is something I forgot to tell you, but it's not a big deal, but it's something you should know. This is called a simple hypothesis. And this is called composite hypothesis. Okay. And I mean, any hypothesis can be composite. The null can be composite too. But typically the null is simple. I mean, by convention and by context, you see why. If you do more stat, you will see why naturally the null is kind of usually simple hypothesis. But okay, so by the way, right, what's simple and what's composite? I think you kind of intuitively know what it means anyway, right? Why you call it simple, why you call it composite. But actually the real meaning, right, or the meaning that's relevant to us is this. A simple hypothesis, I don't care, right, whatever that is, no alternative, is such that the distribution is completely specified. The population distribution, okay, that's what I mean. The population distribution is completely specified under that hypothesis. So here under the norm. But a composite hypothesis means the distribution is not completely specified. That doesn't mean you are not allowed to say that. It's just, you know, technical issue. You just cannot, right? It's not completely specified. Okay. Under no, under the alternative. What's the consequence? The consequence is, suppose you calculate something like this. This can be calculated under a simple hypothesis. Right? Because, you know, basically this translates to mu equals to 1. The same statement, which by the way, right, is the definition of beta, cannot be calculated. Precisely. I mean, because, right, it's not completely specified, so actually the question may be meaningless. But there's a gray area, because here I can still talk about something like this. Under this. All right. In other words, this is still part of the alternative. But this is not all of the alternative, right? Because the alternative is composite. So in other words, if I just abstractly say this, then I cannot really say what it is. But I can still do something like this. So in other words, right, direct access to beta and alpha are only available under the simple hypothesis. Under the composite hypothesis, then you can say, if I specify more, then I can say some part of it. So you can still say something about alpha and beta, but you cannot say precisely what they are. So in this discussion, right? Whoops, here. If I change it to mu positive, for example, then everything I talk about alpha is still correct because I deal with a norm. Everything I talk about beta is still correct as long as it's somehow to deal with alpha, as long as it infer from alpha. The only time when this affects my discussion is when I calculate exact value of beta, which, by the way, I don't think I calculate exactly here. I don't think. You can go back and see my discussion. I don't think at any point I calculate any exact value of beta. Some of them do, right? Like this and this. But these guys don't depend on hypothesis, right? They don't depend on the mu. So that's why their statement still holds. All right. So that's why at the beginning I was trying to do this, but I think that may be a little bit confusing, so I do this. But so that's the last layer of confusion, or I don't know, technicality. But sorry, mu bigger, mu equals to 1. All right. But so don't worry about it so much. All right. I mean, conceptually, just try to see that we can approach it the same way as before. We just don't know exactly what it is in the H1 or in the complex hypothesis, but we can still discuss it. Question? All right, so sorry for keeping you over, and we don't have time to go over the code. We'll do that on Tuesday. All right. I'll answer questions if you have any. If not, then yeah, have a good day. Thank you. You too. Yes, it is.
Professor?
Yep.
I had a question about example 12.2 that we covered in class.
Yep. 12.2, you mean here?
Mm-hmm.
Yep. What about?
So one of the areas that I was having a problem with, and we've done this in the past, it's just that I think I have to review this material again, but how did you go from probability of normal with parameters mu 0 and 1 over n greater than k to the probability of standard normal being greater than k minus mu 0?
Yeah, it's the Z transformation, right? Normal mu sigma square minus mu divided by sigma will be standard normal, right? So here you subtract mu 0 on both sides, and because this is 1 over n, you multiply by
Divide by the root of 1 over, okay, yeah. Okay, this makes sense. Thanks so much, Professor.
Sure.
Yep, have a great weekend.
You too.